Okay, I think we're recording. So we are going to start with that review of last week's material, and then we're going to go on to the hypothesis testing. Okay, so this is what we did last week. So if you guys recall, we have already studied, these are materials that came up like 2 months ago. At the beginning of the semester, we already learned about what's population and what is statistic, and what is the sample. It all boils down to you need to conclude something, you need to learn something about an entire population. But it is never possible. It's really not feasible for us to study it as a whole. So what we do in any case, we take a sample. And from this sample, it's a lot more manageable to compute things from it, which we've already learned. We've already learned how to compute the mean, the sample variance, and all those interesting things. And it's a lot manageable to do that if we only have 30 data points instead of 10 million. But that is not much of use to us. The information about these 30 people, it's not that much useful. Compare that to if, say, you're one data scientist and you're going to try to sell you're trying to get a vendor to sell their products in Indonesia. It's not that much important if you say, hey, these 30 people say they're going to buy your product. It is a lot more useful, it's a lot more meaningful if you can say, hey, you should sell in Indonesia. Indonesians as a whole, the population of Indonesia as a whole would love to buy your products. So this is what we are trying to do with statistical inference. From the sample, the manageable sample that we can count, that we can compute things from, how can we infer something about the general population? Last week, we tried to infer two things. We would like to infer the probability distributions of the sample statistics, and two is the parameters themselves. So first, from the statistics, we have, in this particular picture, we have 5 points, data points, 5 people. Here, I could compute the sample mean, and I can compute the sample variance. There's only 5 data points. I can compute it. You should know how to do it by now because we covered it in the first lecture. But from here, from this information that I do have is actually, how can I get the population mean? How can I get the population variance? So the first thing we did is, what is the probability distribution? So as you know, this is a probability distribution. So what is the probability that the population mean is this value? What is the probability distribution that the population mean is at this value? And we model it as a standard normal distribution because we need to approximate it somehow. So that's what we did in the 2 weeks ago in distribution of sampling statistics. And the second thing that we did, that's the first one, infer the probability distributions. The second one is, I don't really want to know the probability. I don't simply want to know what's the probability of it being 84. No, I want to actually determine the value itself. So if this is 84, what is the probability one? Is it, I don't want to know the probability of it being 84, sorry, mu being 84, but instead the second one, this is the first one, the second one, I want to know if this is 84, is the population mean 85 exactly? Is it 87 exactly? What is the exact value? So in the first one, we only get the probability. The second one, we want to get the actual value. So we're going to repeat this briefly in the initial slides. So this is part 1. So for part 1, my sample, I have a mean. How is it distributed? What's the probability of the actual mean being on this value here? What's the probability of it being this value here? And so forth. Here are some assumptions that we use in order to compute it. So since you guys have already been familiar with the concept of random variables, we now model every single data point as a random variable. And we assume that it will follow some sort of distribution. So if it is some sort of distribution, the sample data that we take should also follow that same distribution, roughly. So using those, we can infer, using the central limit theory, some basic distributions of these combination of samples. Obviously, it might not be exactly normal, but we're going to use the normal distribution as the best approximation due to, obviously, the normal distribution is, I've mentioned this so many times during the semester, most things can be modeled based on a normal distribution, or at least approximated by a normal distribution. Second of all, we've already learned in this chapter that any underlying distribution, be it Bernoulli, be it exponential, be it anything, if you have enough samples, it will then look like, I'm trying to find an English word for menyerupai, sorry, blanked out there for a sec. Whatever underlying distribution it does have, if you have enough data points, it will be similar, it will look like a normal distribution. So these are the two reasons why we're trying to approximate it using a normal distribution. Based on the central limit theorem, we know that the sum of data points will follow this distribution, this normal distribution with the parameters n mu and n variance. So based on the central limit theorem, we can then conclude that if we want, sorry, if we want to compute the distribution of the sample mean, we know that we can approximate it using a normal distribution like this. And to normalize it, we can use a standard normal distribution like this. Meanwhile, for the sample variance, we have realized that the expected value of the sample variance, so if you have a sample, you take its variance S squared, and you take the expectation value, that will bring you to the population variance. Detailed derivation of all of that we covered in the distribution of sampling statistics. I think someone just unmuted themselves. Is there a question? Good timing, because that's the end of the first review. So I'll give you a pause there to maybe get that in your head a bit. And if there are any questions, go ahead. I didn't quite catch who it was that unmuted themselves for a sec. So if you do have a question, please unmute yourself again or write it in the chat box. I didn't quite catch who it was just now. There wasn't any questions? Okay, am I safe to move on? Can I please get some feedback if it's okay to move on, or would you like more a longer pause to review that in your heads? Anyone?
I think it's okay, Miss.
Okay. Okay then. So I'll just continue. Once again, I'll remind you that you are allowed to unmute yourself at any time if you have a question. Okay, so we already did that in the first part in distribution of sampling statistics. And now for the parameter estimation part. We're going to go back to the same graphic that we have. Once again, we have a population, but we cannot study it realistically, so we're going to study the sample instead. So as we know, in the previous chapter, we only estimated the probability distribution. So like what values are probable? How possible is it to have the value of 0.7? Well, how probable is it? How is the probability of the mean having a value of 0.8 and so forth? Oh, okay, apologies. There was just someone, like, those sellers passing by. So I turned on my noise removal software. Okay, where were we? So previously, we only computed the probability of every value, of certain values being the mean and so forth. But now I don't want to know the probability. I want to know the exact value. So in order to do that, I need to take some estimators from the sample. So I need to take some statistics that I can use to estimate the parameter itself. Like, for example, I can take the sample mean in order for me to deduce something about the population mean. I can take the sample variance to deduce something about the population variance. So in order to determine these estimators, we have something called the maximum likelihood method. Sometimes you can find references calling this the maximum likelihood estimation, maximum likelihood theorem, and others. So one thing that I would like to remind you here is that when I say that I am estimating some parameter using a sample mean of 2.5, for example, please distinguish the two terms of estimator versus estimate. So in this case, the estimator is the sample mean, and the value itself, 2.5, is the estimate. So using this estimator that I have, I then want to compute the population mean. So we are using here intervals to estimate the value. I'm going to give you an illustration why in the next slide. So actually, the sample mean itself, X bar, is the maximum likelihood estimator of mu, or population mean. So what does this mean? This means that if I compute the mean GPA of this class of Statprob and say it comes out as 3.2, that means that this sample mean is actually a very good estimate to the GPA of all 2000 of all Facilcom students. So why don't we just use it as is then? Why don't we just, okay, then the mean of the sample equals the mean of the population? Because actually in any type of statistical computation, we never expect that it will be exact. It's just impossible because of the variability, because I could take this class as my sample. I could take 3 random Toki students. I could take 6 students in the 2016 cohort that are already graduated. So since the sample that I take is very, very different, they are very heterogeneous. I can take very different types of samples. So I know that I will never actually get an accurate estimate, but I know that it will probably be close. But what does close mean? If it's only close, I never know how wrong I am. I never know that, oh, you're only like 2 points, 0.2 points GPA off of the correct estimate. Is it 0.2 or is it 0.02? I never actually know how close my estimate is. Like this is the example. I just use an example of GPA, but here we have an additional example about weights of students. If the sample says the average is 65 kilograms, if I were to be very naive, I can just estimate the population mean to be 65 as well. But I know it's not accurate uh, as expected, but I don't have any additional information. I don't know how wrong I am. Is it off by 1 kilo? Am I off by 5 kilos? How close was my estimate actually to the real deal? So that way, in order to get around this, we can use interval estimates. It gives me a little bit of leeway. It gives me some buffer zone. It gives me some wiggle room for me to be more confident about my answer. I know that I'm not that wrong. I'm not that off of the correct estimate. So instead of saying exactly the weight is 65, why don't I say it's between 60 and 70? I'm more confident that this answer is a lot more true, it's a lot more accurate, and it's a lot more statistically responsible to say the mean is between 60 and 70 compared to if I say the mean is 65. I have more chances to be wrong if I only give you one value, but if I give you a range of values, I have more chance to be correct. So that is why we use interval estimates. Short pause here. Any questions? Okay, I don't see there are any questions. So this is what it means to have a 101 minus alpha % confidence interval. Recall when I just talked about the intervals just now, I wanted to be more confident about what I'm saying. I want to have more chance of being correct with the facts that I present. So for example here, for my 101 minus alpha confidence interval, I want to specify this interval in which I am this confident, 95% confident, 90% confident, and so forth. So my target is I want to give you an accurate interval with the most confidence that I can. So I want to be, of course, I don't want to be wrong. So in order to do that, I need to determine beforehand, how confident do I want to be? Do I want to be 95% confident? Do I want to be 99% confident, and so forth? So what happens is, if I am 99% confident, that means that my interval will be larger because I want to be I want to be a little bit, I want to have a buffer to be wrong. But if I want to have a 90% confidence interval, that means I can define a shorter interval because it's okay, I have 10% possibility to be wrong anyway. So what does this actually mean? So what happens is when I want to construct the confidence interval, so here, say I'm trying to estimate the mu or the population mean. Say here I'm trying to estimate the population mean. So how can I do that? Say I have these different samples. So if I take one sample, this is my confidence interval, this one here. If I take a different sample, this is my confidence interval here, and so forth. So every time I take a different sample, I get a different confidence interval. Makes sense, right? When you think about GPA, I might get different results if I ask this class, if I ask a different class, if I ask students that are about to graduate, the estimate that I will get will be different. There will have different intervals of my estimate for average GPA. So what we mean here is that from all of these trials that I do, so if that is the real mean or the real population mean, and this is the sample mean of every single one of these blue lines is the sample mean, pay attention. that here I have one confidence interval that actually does not really contain the correct mu. So here we know that every time I construct a confidence interval, I may not actually encompass the correct mu. But I want to be quite confident 95% of the time that my interval does encompass the real mu. So in order to get this concept really in your head, I'm going to give you a small mini quiz. So if I say I have 95% confidence interval, by the way, if I say 95%, then obviously my alpha will be 0.05, right? 1 minus 0.05. Yeah. So if I say 95%, this is 100. 1 minus the alpha 0.05. Let's see, did I just blank out? No, that's correct. So this is the correlation between the alpha and the degree of confidence. I'm going to give you guys around 1 minute to look through this problem. And I want you to decide which one is the correct statement. When I say, sorry, that the population mean of whatever statistic that I am computing falls between 7.28 and 10.72, what does that mean if I say I have 99% confidence? Does it mean that the mu is within this proposed interval? The probability of the mu being in my interval is 99% or 0.99? Or does it mean that if I take repeated samples, I take different samples of the population, 99% of the time, the intervals will contain the population mean, and 1% will be this one here that does not contain the population mean. Give you a chance to think that out. Okay, I'm not going to tell you the answer, but I would like you to remember this question because we're going to go back to this at the end of the review. Okay, so now that we know the meaning of a confidence interval, so now we're going to learn how to actually compute those intervals. So obviously, it's not like I can take any estimator and use it to estimate any parameter that I want. No, there is a limit as to what we are able to do. And these are the cases that we can compute, that we can estimate the parameters from. So I can compute the interval, the confidence interval of the normal mean if the variance is known. I can also compute it if the variance is unknown. This is assuming one normal population. If I have two normal populations, I can compute the confidence interval of the difference of mean if the variances are known or unknown but equal. And lastly, the first two cases are for normal population. The last one is if we have a Bernoulli population, I can then compute the confidence interval for the mean of the Bernoulli random variable. I'm not going to go through them in detail, but here they're coded. By the way, I have already uploaded, I've re-uploaded the PDF of the slides on Skele with this color code to make you to make it clear for you which case is which. So there's pink, there's purple, there's green, there's blue, and yellow. And here, just as a review, these are the ways, the formulas to compute it when the variance is known, the variance is unknown, two populations when the variance is known, and where the variance is unknown but equal, and for the Bernoulli population. Any questions? Take a pause. Any questions? You can use the chat box if you want. Not yet? Okay. So I'll direct all of you to this Google Forms in the chat box. So if you would please go to the link that I have provided in the chat box. And we are going to recap the inferential statistics portion of these two chapters. Don't forget to write down your NPM. This participation in this Google Forms will also serve as attendance for this class. So let's go through it together. I'll wait. I hope you guys have already accessed it though. I'll close it after we go through it together. Okay, so first of all, please, after you put in your NPM, you can go to the first question on your Google form, and please tell me what you think about this confidence interval question. So here, this is my NPM, for example. First question, feel free to select this, the answer that you think is correct. What do you think is the correct interpretation for the confidence? Go ahead and fill it out. I'll give you some time to think.
Miss, we can hear your voice.
Sorry, since when, Zahran? Sorry.
I believe it's since number 2.
Okay.
Right.
Okay, apologies. So I just sent you guys. Did you catch me saying that I sent you guys a link through chat,
Not yet, I guess.
or you just assumed so because I sent it?
Yeah, that one.
Okay, I'm sorry. Okay, guys. So there's two links on the on chat. So the first one is Google Form, and the second one is independent reading. So it helped out a lot of other students previously in this class to understand the difference. So my question is, what's the difference between distribution of sampling statistics and parameter estimation? We already covered this briefly in the beginning of the class. I've given you one reference that you can read to get a better understanding, but I want to know the answer in your words. Please write what's the difference of these two things in your own words. You can also use the reference. I'm going to give you a little bit more time here, maybe around 3 minutes to complete this answer. Don't be too worried. I'm not going to grade you on this, but participation will count as the attendance. So go ahead. I'll give you around 3 minutes for this question here. Okay, I hope that's enough time to formulate your answer. Okay, I hope that's enough for reading. I'll give you an additional 2 more minutes perhaps to write down your answer. Don't worry, it's not a test. Just write down as long as it's your own words. Do not copy it, please, from the reference that I've given you. Okay, if you are done, I'm going to direct you to the next one. So the next the next trigger I'd like to give you is what usages can you think of? Like, in what case do you think it might be useful for us to either estimate the distribution or parameter estimation? Um, I believe last week we covered one example, which was when you see statistics on the internet, you know that a lot of the time it's a hoax. It's not really true. So you can use the distribution of sampling statistics to check, is this thing that I just read, is this believable? Like, what is the probability that from the sample, what's the probability that the population parameter actually does fall in this interval? Is it a large percentage? Is it a low percentage? So it'll help me be able to distinguish what's true and what's not on the internet. Now I want to know, what do you guys think? In what case do you think it might be useful for us to do this in real life? Okay, I hope that's enough time for you to think of an example. So I'll invite you guys to go on to the next and last page. So for the last page, this is more of a reflection, an internal reflection for all of you. I'd like you guys to fill in what is the most interesting thing you've learned about these two topics. What's the most difficult thing about these two topics? And the last question is obviously a trigger for us to move into the next topic. So please fill it out. And when you're done, you can please submit your answers through Google Forms. To fill this out, I'll give you around 5 minutes. And after that, I will close this Google Forms. Once again, I'll remind you that this will serve as your attendance today. So I'll see you in 5 minutes. I have a question here from the chat from Aska. Let me try to clarify it. So, do you think that in real life, this is an open-ended question. Don't worry so much, Aska. It's kind of just a trigger to the next material. So, like up until now, we have tried to estimate the values of the population's parameters, but does it actually do you much good if you know, oh, the population mean is 6.5? Do you think it might be more useful to use that for a higher order decision? Like, for example, if the mean is 6.5, why don't I try selling this product in Indonesia? That's what I mean. Do you think it might be useful to use it not as is, not just like it's a data point 6.5, but instead use it for deciding something else? I hope that's clear. Okay, on my clock, it is 14:26. So last minute submissions. This is not going to be graded, so I'll wait a bit. Feel free to, submit your answers, and I'm going to close it in 5, 4, 3, 2, 1.5 and a quarter. How many people are here? There are 22 people. I've only have 18 responses. A quarter, a fifth, a sixth. Okay, I'm going to close it. Okay, guys, I hope everyone has already submitted their answers. Don't worry, it's not a quiz, not going to grade you. It's just for attendance and reflection. Okay, it's closed. So as a short review, among all of the questions that I gave you in this reflection, there's only one that has a correct answer. Everything else is more of an open understanding and brainstorming question, except, wrong window, sorry. Except this question. This one actually has a correct and incorrect answer. So as mentioned, in this case, I can construct a confidence interval for every sample that I take. So if I take sample 5 people from over here, I have the sample mean, and then I construct the interval, the confidence interval of population mean. Then I take another 10 people from this side. I construct the sample mean, and then I construct the confidence interval for the population mean. And then tomorrow I take another 16 people on this side. I compute the sample mean, and then from that I can construct the confidence interval of the population mean. This means that from my 3 samples, I obtain 3 different interval estimates for population mean. Which one is correct? All of them are correct, but all of them may not necessarily contain the correct population mean. However, when I say that I am 95% confident, that means if I say 95% confident, that means I used an alpha of 0.05 in my formulation. And I know that from the repeated samples that I took, in this case, I only took 3, from the different samples I took, I know that if I have 99% confidence, 99% of the time, my confidence interval will contain the correct mu, or correct population mean. That means if I took 100 different samples, 99 of the confidence intervals constructed from those samples will contain the correct mu. However, there is one sample where it does not contain the correct population mean mu, which is this little guy over here. So I take one sample, I get this interval. Oh yes, it's correct. It contains the correct mu. I take another sample. Oh, here is the confidence interval. Oh, it's correct. It does contain the mu, and so forth. For 99 times, I will have it correct. But for that one single sample among 100, it does not contain the correct mu. Okay. Now we can move on to hypothesis testing. So in hypothesis testing, it has something to do with the last question I asked on your inference reflection. So in the last chapters, we have a computed statistic from the sample. And from that, I infer the value or the probability of the equivalent parameter in the population. As an example, from the average GPA of Ferdi, Bagus, and Zahran, you guys are on my screen, sorry, no intention there. I can then infer the roughly the average GPA of all Fasilkom students. Or I can also estimate the probability distribution of average GPA of Fasilkom students. So up until now, we haven't done anything with that data point. We've only inferred what the value is. I only know that from this average, I get the general population average of 3.2. But so what? We need to use this for something more important, like something more meaningful. So this is what we're going to do in hypothesis testing. Does not mean that estimating the actual value is useless. No, so please don't get that mixed up. But in real life applications, usually when you're being a data scientist in e-commerce company, they're not going to ask you, hey, what's the average spending of visitors to our website? They will then use that data. Oh, usually people spend between 1 million to 1.5 million a month. But instead of that, they're going, instead of using that value on its own, in order to make decisions for the company, they're going to ask you like, oh, does that mean that this product does not bring any revenue? Does this mean that we need to eliminate the bonuses of purchases? So this is what we're going to do in this chapter. We're going to bring it up one more semantic level, one more semantic, yes, semantic, yes, semantic level. We are going to try to infer a decision from the values we took. So what we did in the last two chapters, arguably, is the first step of what we do in inferential statistics. So because in a lot of applications, you don't really need to know the exact values. But what you do want is using that values to decide something or to test a particular hypothesis concerning the parameters. My question here is, what exactly is a hypothesis? So a hypothesis itself has this definition. I presume that since this is the international class, you probably have already met this terminology before somewhere, maybe reading a novel. And I do believe you have a general gist as to what it means. So it's a conjecture, it's a guess, it's a, it's a status, it's a fact that you presume about a population parameter. Like, for example, is the average spending on this website 1 million? Or on the other hand, is the average spending on this website less than 1 million? And so forth. This allows you to make business intelligence decisions. So in order for us to do that, we are going to learn about the test itself, which is hypothesis testing. So for hypothesis testing, what you're actually doing is that when you have a survey, when you have an experiment and you get up the results, you need to figure out if these results that you obtained, did you actually get them by chance? Is it just a coincidence? Why is this significant? This is significant because if your results are just by chance, if they are random, this experiment will not be repeatable and it has little use. So it doesn't really matter if the mean is 6.5 this time, because that's just a number that came up randomly, coincidentally. We want to know if this experiment actually follows some sort of rule so that we can infer a decision from it. Here we have the same case as previously. We have either one sample case or a two sample case. So we can model the problem in two ways, like the one that I said first, is the average spending 1 million? Or here, is the age of Indonesian population, is it 50? Is the mean of IPK of IP students, UI students 3.1? Or do I have two populations in which I say, is the mean of Fasilkom students higher than FHUI students? So you might notice a pattern here. When we were computing the parameter estimates in the last chapter, we also divided the cases between one population and two populations. This is the same. We either have one population or two populations. You're going to find a pattern coming up in this chapter as well. So in order to understand about hypothesis testing, we have some terminologies or elements that we need to go over. I'll give you some time to look through these because I think you might already know what they are. So a brief pause here for 30 seconds-ish for you to go through these terminologies and remember, maybe you've already met these terms before. Okay, so hopefully you've looked through these, and we're going to go through them one by one. So the first one is the null hypothesis, which we usually write as HO. Note that it's only written as HO. There's usually no other way for you to write it. Please don't write it H something else. It should be written as H0. This is the null hypothesis, which means this is the hypothesis of no difference. And it is the hypothesis that we want to test. This is what we are going to test. Is it true or is it not? And it is often, note that I have bold the word often. It is often the hypothesis we wish to disprove. Not necessarily, not always, but often. And for example, here, when I say that the mean, I want to test if it's the mean of IPK UI students is 3.1. Thus, the H0 that I want to compute is it correct? There's no difference. Is it correct that the null hypothesis is my mu, or the population mean is 3.1? Is it correct or is it not? So if we have a null hypothesis, obviously we need to have the opposite. That is the alternative hypothesis. If previously we were very rigid with the null hypothesis, it must be written HO, H0. Here for the alternative hypothesis, you have some leeway. You can write it HA, H1. Most commonly is HA and H1, but in theory, you can write it as anything aside from H0. You can write HB or so forth. I have not found a literature that that does not allow you to do so. So here you have some leeway, although I must remind you that the most common, the rule of thumb is to use A or 1. And this hypothesis covers everything else not covered by the null hypothesis. This is the research hypothesis, which is supported by rejecting the null hypothesis. So usually when you want to prove something, you prove that the H0 is false, thus accepting the alternate hypothesis. It's kind of like the indirect proof that you have probably already learned in discrete mathematics. So if previously our H0 in the previous example here, our null hypothesis when we were trying to study the mean of IPK, the mean IPK of students is 3.1. So if my null hypothesis is the mean is equal to 3.1, then the opposite is obviously the mean is not 3.1. But be careful, the way you can denote that it is not 3.1, there's two ways. The first one is non-directional or two-tailed test. Please don't confuse this with the previous one, two-sided CI. This is a two-tailed test. So in here, if previously our H0, I shouldn't have used red, by the way, you can't really see that. So let me repeat that. So if we say that our null hypothesis is the mu is equal to 3.1, then if I have a non-directional test, the opposite of it, the alternate hypothesis, is simply that the mu is not equal to 3.1. This is quite straightforward. This one is equal, and this one is not equal. But if you have a directional test, that means you want to know, okay, it's not 3.1, but in which direction does it go then? So your alternate hypothesis would be either, is my mu larger than 3.1 or less than 3.1? So arguably, if you have a directional test, you get more insight on what the value actually is. Because on the non-directional test, you just simply know that it's not true. But here you know in which direction does it go. So now we have the null hypothesis and we have the alternative hypothesis. But how can we prove it wrong? So just like the previous chapters, we are trying to infer something about the population from the sample, because you cannot really compute the mean of the population yourself. So what we do is we compute the statistic from the sample. And this is then used to either reject or accept the null hypothesis. So in theory, the test statistic that you use, that you compute from the sample, can be any statistic that can be computed. It can be the mean, it can be the variance, and it can be the standard deviation. But in reality, a lot of the times it's a combination of these, as well as there are some rules as to what type of statistics you can actually use to test your hypothesis. Okay, so now you have your test statistics of your sample. You use this to either reject or accept your null hypothesis. But obviously, you don't always get a correct estimation. So in the decision-making process, you will sometimes encounter some errors. So if you recall, we can form this confusion matrix. You might want to recall this terminology because you might meet this confusion matrix again in data science related courses. So in errors will happen when, for example, you reject the null hypothesis while it's actually true. So this is the correct decision. You really should reject the HO if it is indeed false. Of course, that is the ideal way. On the other hand, you should not reject the HO if it is actually true. So this is straightforward. When HO is false, reject it. When HO is true, do not reject it. I hope I don't need to explain that. But in reality, you don't always get a correct answer, and you might reject HO even when it is true, or type 1 error, or you might not reject it when it is actually false. And this is the type 2 error. So obviously, this is a trade-off. You might have more type 1 error and less type 2 error in some cases, or the other way around. And you cannot really determine which error is a worse error to make, because it depends on what you're trying to prove. So this is a balancing act. If you go on and study machine learning or this data science or other types of learning-based courses, you'll realize that this trade-off will happen all the time. So just so you know that here is a balancing act, I guess you can say. And obviously, when you're estimating, you will never have an ideal condition. So just like when you're computing the confidence interval, you need a level of confidence. And in other words, you need to determine the level of significance. And in the case of hypothesis testing, what does it mean to have a certain level of significance? 0.05, 0.01. These are the most commonly used values. It means that when you say 0.01, level of significance, it means that when you reject HO, I know that I might be incorrect 1% of the time. I know I might be incorrect 5% of the time, depending on the level that you choose. So when you say that you reject this null hypothesis at 0.05 level of significance, that means the difference between the observed statistic and the actual value of the parameter is significant at that level. You can say it that. So unless defined otherwise, the level of significance that you should use should either be 0.05 or 0.01. Same case in confidence intervals, you should either use 95, 90, or 99. These are some basic numbers that you should remember. I don't require you to memorize it, but this is the rule of thumb. These are the numbers that are usually used. So if it's not specified, you may write down your assumption, like assuming a level of significance alpha of 0.05. Feel free to write your assumption if it's not specified in the. Okay, so if you recall these concepts, I'll give you some time to look at this graph while I take a drink break, and I'll get back to you in a second. Okay, so I hope you guys remember that I emphasized when we were talking about normal distributions, chi-square and t distributions and so forth. I emphasized that I hope you understand the difference between the graph's shape, critical value, and area under the curve. So the level of significance, say 0.05, is a proportion of the population. So in this case, this is the rejection region. So this is the corresponding to the alpha. It's the proportion of the area that falls into these two tails. On the other hand, the critical value is where I draw that line. So like, for example, a level of significance 0.05, that means if I have a two tail, I have to divide it into two. So I have 0.025 on this side and 0.025 on that side. So what I want to do is I need to be able to determine the critical value, the number at which I need to draw this line so that the area on the right-hand side corresponds correctly to this much of the population, this proportion of the population. And why is this significant? Is that if my test statistic falls in the rejection region, then I reject my HO. That is the whole point. I need to compute the test statistic. Where does it fall? Is it in the rejection region? If so, then I reject my HO. So to correlate it with the critical values, I'm going to direct you back to when we were studying about the distributions. I hope you remember the difference between critical value and the proportion of the population. So, okay, now using this graph, we now have the areas of rejection. We also have the areas of non-rejection, which are delimited by the critical value. So here, like just now when I gave you an example, I divided the alpha into two. I can do that if I have a two-tailed test, or if I have a directional test, I only have one tail or one side only. So the first one is the one-tailed test. So as denoted on this example, when the alternative hypothesis is directional, so if following the example we had just now, if I have H0 is the mu equals 3.1, and I have an alternate hypothesis that is directional, so mu is less than 3.1, for example. So I know that if my test statistic falls in this region, that means I need to reject it, and everything else falls in this area. This is a directional alternative. So here we have a directional alternative. This is called a one-tailed test. Note that in this case, when I use an alpha of 0.05, this entire region will correspond to a proportion 0.05. Obviously, the opposite is a two-tailed test. So if in the example that I have just now, when I have a HO of mu equals 3.1, my alternative is not directional. In other words, the mu is not equal to 3.1, and thus I can I just need to know if it falls into this area or that area, then I will reject it. In this case, note that there are two tails. So when I use an alpha of 0.05, for example, the rejection region must be divided in two, and thus this area will correspond to 0.025, and this area will correspond to 0.025 proportion of the population. So this is non-directional or two-tailed. Short pause. Any questions? Okay, so I realized that the explanation that we just did in class was just now, was a lot of theory. So I'm going to give you guys a respite, a short break, if you will, by showing someone that might be a lot more interesting than me. Give me a second, sorry. I hope you guys can relax a little bit, and we're going to look at this video together. I hope this can give you a more relaxed version of events, if you will. Okay.
There are 4 steps in data-driven decision making. First, you must formulate a hypothesis. Second, once you have formulated a hypothesis, you will have to find the right test for your hypothesis. Third, you execute the test. And fourth, you make a decision based on the result. Let's start from the beginning. What is a hypothesis? Though there are many ways to define it, the most intuitive I've seen is: a hypothesis is an idea that can be tested. This is not the formal definition, but it explains the point very well. So, if I tell you that apples in New York are expensive, this is an idea or a statement, but is not testable until I have something to compare it with. For instance, if I define expensive as any price higher than $1.75 per pound, then it immediately becomes a hypothesis. Alright, what's something that cannot be tested with a hypothesis? An example may be: would the USA do better or worse under a Clinton administration compared to a Trump administration? Statistically speaking, this is an idea, but there is no data to test it. Therefore, it cannot be a hypothesis of a statistical test. Actually, it is more likely to be a topic of another discipline. Conversely, in statistics, we may compare different US presidencies that have already been completed, such as the Obama administration and the Bush administration, as we have data on both. Alright, let's get out of politics and get into hypotheses. Here's a simple topic that can be tested. According to Glassdoor, the popular salary information website, the mean data scientist salary in the US is $113,000. So, we want to test if their estimate is correct. There are 2 hypotheses that are made: the null hypothesis, denoted H0, and the alternative hypothesis, denoted H1 or HA. The null hypothesis is the one to be tested, and the alternative is everything else. In our example, the null hypothesis would be: the mean data scientist salary is $113,000, while the alternative, the mean data scientist salary is not $113,000. Now, you would want to check if 113,000 is close enough to the true mean predicted by our sample. In case it is, you would accept the null hypothesis. Otherwise, you would reject the null hypothesis. The concept of the null hypothesis is similar to innocent until proven guilty. We assume that the mean salary is $113,000, and we try to prove otherwise. Alright, this was an example of a two-sided or a two-tailed test. You can also form one-sided or one-tailed tests. Say your friend Paul told you that he thinks data scientists earn more than $125,000 per year. You doubt him, so you design a test to see who's right. The null hypothesis of this test would be the mean data scientist salary is more than $125,000. The alternative will cover everything else. Thus, the mean data scientist salary is less than or equal to $125,000. It is important to note that outcomes of tests refer to the population parameter rather than the sample statistic. As such, the result that we get is for the population. Another crucial consideration is that generally, the researcher is trying to reject the null hypothesis. Think about the null hypothesis as the status quo, and the alternative as the change or innovation that challenges that status quo. In our example, Paul was representing the status quo, which we were challenging.
For more videos like this one, please subscribe.
Okay. Brief pause, 1 minute to take that in. And once again, I invite you guys, if you have any questions at all. Maybe via the chat box, perhaps, if you don't want to unmute your mic. Okay, I guess not. So I'm going to continue to, because just now we had the short definition from the video. I hope the concept is clear to you. But in this course, we have a specific number of steps that we require you to follow while completing these types of problems. And I'm going to go through them with you now. So the main difference here is it's the same thing, actually. You have to go through these steps in order for us to be able to determine if we reject or if we accept the null hypothesis. So these are 5 steps that we have defined here. Just now, I think there were 4 on the video. So please take into consideration this one. So here is the first step. First, you need to state the hypothesis. So obviously, you need to define both the null hypothesis and the alternative hypothesis. So if you have a non-directional alternate, then you just need to do H0, H null equals something, and HA doesn't equal something. For the directional one, then you need to determine H null is something and HA is either less than or larger than. So I realize that it's quite, the challenge is actually usually interpreting the problem, the sentences, into the correct equations. So to help you out, I've copied here common phrases rule of thumb. So these words are often used when in problems to describe what you're supposed to be proving. So these are some alternatives that you might find in some problems. So I'd like to remind you that this first step is of utmost importance. I have found that sometimes a lot of students compute the hypothesis testing and have a conclusion without actually stating the initial hypothesis. This is big error because you have to determine from the beginning what is your alternative hypothesis, what is your null hypothesis, what are you actually computing. So please don't forget this step. The second step is you need to set the criteria of rejecting, like what is the limit, what is the critical value, what is the limit that you're going to determine, in which if your statistic falls in that area, you are going to reject it. So first you need to set the level of significance. So you need to determine alpha you're going to use. Once again, I'll remind you that most commonly used values are 0.05 and 0.01. And if not given, you can assume one of these two. And then you need to find the critical values for that level of significance. So you will need to either use the Z or T distributions that we've already covered in normal random variables. So you need to know what's the critical value, what is the value on which we draw the line so that this area on this side will be rejected. So you either need to divide it into two tails. So you divide the alpha into two, or you just use it as is for a one-tailed directional HA. Next is set the criterion for rejecting H null. So this is where it changes. If you know the variance, that means you can form a standard normal distribution, and you can use a z-score or the standard table. But if you do not know the variance or the standard deviation, that means you cannot assume a normal distribution, and you should use the t-score. If you recall, when we were covering the chi-square and all that, I mentioned that you will need t-scores and z-scores most often. So please don't forget the standard normal table as well as the t-table. I have given you some links on Scale of some good tables that you should use as your reference. Next step is to construct the confidence interval of the parameter that you are trying to estimate. Hey, we learned this in last chapter. That means I don't need to explain it to you again. We've already learned how to construct these confidence interval, how to estimate the interval of the correct parameter. I'd like to put a note here that you do not necessarily need to compute the confidence interval to take a conclusion, to make a conclusion on your hypothesis. It's to give you a better understanding overall, to give your hypothesis testing weight, to be more convincing in your hypothesis testing results. So this step is not it's not absolute. You don't have to have it to actually make a conclusion. But in this course, we encourage you to do so to get a better understanding on how the statistics behave. And lastly, you need to interpret the results. Do you decide to reject it, or do you decide to accept it or not reject it? Okay, just now I said something and I hope you paid attention. I said accept, and then I corrected myself, do not reject. So this is one tricky semantic thing about hypothesis testing. So if it falls in the rejection region, you can simply say, I reject H null. That means that my null hypothesis is incorrect, I reject it. However, if it's the other way around, your statistic does not fall in the rejection region. If you want to be very particular about the terminology, it does not immediately mean that you accept H null as correct, but you do not reject H null. So I'm not going to go too deep into it. I'm just going to mention it to you so you realize that there is a difference here. But even statisticians, data scientists have not really, there are so many different opinions out there as to what it actually means to say do not reject. Does it mean accept, or it just says do not reject? So I would like you guys to maybe internalize that point. And as long as you understand that there's a difference, that's enough for this course. So I'm going to give you one sample here. So as I mentioned, we have different cases, right? You either have one population or two populations. For one population, you either know the standard deviation variance or you don't know it. So in this case, when you have one normal population and you know the alpha, not alpha, sorry, the variance, then you have these elements of your hypothesis testing. So as a standard, your null hypothesis will either be equal to something and your alternate hypothesis would be not equal to that. So here, when you go to the directional one, here we have a little bit of modification. So if your alternate hypothesis is larger than, that means for your null hypothesis, not only do you say equal, but you also say less than, and so forth. And the test statistic that you compute to determine if it's rejected or not is this combination here. N is the number of samples you have, number of samples. Obviously, this is X bar. This is your sample mean. Mu 0 is the value that you're currently computing, and this is the standard deviation of the population, because here you have the standard deviation of population. It is known. And what you need to what you need to determine is the criteria of rejection is if the test statistics is larger than that, or if it's larger than this, and so forth. We're going to go into one sample here. So here we have, let's put this away so I can write down. So let's see what we have in this example. So this psychologist wants to test and measure the self-confidence of 50 professional athletes. His theory is, this theory is about the population. Professional athletes tend to be more confident than others. So if the national norm of the test, so the average of the test is 72, we know that the standard deviation is 13.3. So here we already know that we fall into the category of one population, which is professional athletes. And we also have, not for people in general, sorry. And we also know that we have information about the standard deviation. Using the sample mean of this, we want to know if that theory is true using this specific significance. So this is the explicit information we have. We have an N of 50, a sample of 50. We have a sample mean of 74.1 here. We have the population mean, 72. We also have the population standard deviation, and we also have alpha. So let's go through the steps that we need to do to test our hypothesis. I like to draw out the steps when I'm solving these types of problems. So like, for example, first step is state the hypothesis. So here, what is the theory that the psychologist has? He says that professional athletes tend to be more self-confident than others. So I need to prove the opposite of that. So if my alternate hypothesis is that the mean will be larger than 72. Why larger? Because the theory is that the professional athletes tend to be more self-confident. So I can presume that they should score higher than the average of people. And the null hypothesis is the hypothesis of no difference. Thus, the mean population of athletes should be less and equal to 72. Or I could alternately write this as mean equals to 72. I personally like to follow less than, and equal. So that's my first step. My second step is I need to determine the test statistic. So, oops, I don't remember the equation. See, I will not expect you to remember the equation either. So first, on the test statistic, I will compute it in, what's my test statistic? It is in z-score notation. Here it is. I think actually I've already computed it. Let's see, have I computed it? Oh, yes. Here, because it's already past 3 o'clock, I'm just going to show you then the solution. And once again, I don't like this very much. I personally will understand it better if we use less and equal than. And then based on the test statistic, then we can compute the test statistic as follows. In this solution, it was kind of mixed up. Usually this is first step, this is the second step, this is the third step. So now after we compute the test statistic, we know that the test statistic is 1.12. And based on the rejection region, I know that my, I'll draw it out for you. This is my standard normal distribution. I know the standard deviation, so I can use a z distribution. And since it is a directional alternate hypothesis, that means I don't need to divide the alpha into 2. So I just simply can just do that. I need to know, this is my alpha here, my alpha corresponding to 0.05 of the population, or 5% of the population. At what line do I draw this line? Since this is a standard normal distribution, it'll be the same for 0.05. You can check on the z-score table. This will be equal to 1.645. You guys will notice, since I already mentioned that alphas will be either 0.05 or 0.01, that means if I'm using a two-tailed, then I'll only need to find either 0.005 or z 0.025, and in this case 0.01 or z 0.01. So since these are always the same values anyway, you guys should look them up beforehand. Last year, these values were given in the test. So it's good to know these values as common knowledge. For example, Z005 is always equal to 1645, and so forth. And so now, since it's directional, my rejection region, following this equation here, I need to reject it. So we have, this is the case that we're currently doing, this one here. I need to reject my hypothesis if the test statistic is larger than ZA. So my ZA is 1.645. I need to reject it if my test statistic is larger than this. After computing my test statistic, I realize that 112 larger than 1645. Nope, it is not larger than. Since it does not fall into the rejection region, then I conclude that we cannot reject H null, or we accept H null. Pause. Any questions? Chat box, any questions? Okay, if not, then I'm just going to go through all the other scenarios briefly. So just now, we had one population and a known standard deviation. Obviously, the opposite is when I have one population, oops, but the standard deviation / variance is unknown. In this case, the steps are exactly the same. You need to state your hypothesis, you need to compute your test statistic, you need to determine your rejection region. But if you do not know the standard deviation, that means you cannot use the standard normal distribution. And on the other hand, you need to use the t distribution. Here we have a brief refresher on what the t distribution is. And we have this table that tells you how to compute every step of your hypothesis testing. You need to determine your hypothesis, then you need to compute your test statistic. Note here that we are no longer using sigma because we don't know it, it's unknown, and instead we use the sample standard deviation. And the next steps are the same. You reject it if it falls into these categories. The only difference between the previous example and now is because at this time we use the T table instead of the Z table. We have some examples on your slides. You can check them out yourself. So as a recap, up until now, we've all estimated mu from one normal population. Here we have two cases, either when the variance / standard deviation is known and when it is not known. The only difference is here you use the Z table, here you use the T table. Just like last chapter, we don't only consider one normal population, but we also can consider two normal populations. And the cases where we have two normal populations are the same with the previous chapter, either when we know the variance or when we don't know them, but we know that they are equal. So in the following slides, you can find the different computations. So here, if you know the known variances, use this test statistic and reject it if as follows on the right-hand side. Or on the other hand, if you do not know the variances, but you know they're equal, use that test statistic on the left-hand side, which is a lot complex, and use the rejection criteria on the right-hand side. So once again, the difference between known and unknown variances is if you know it, you use the z-scores, the Z table, and if you don't know it, you use the T table instead. So here we have 4 different cases that we can compute the hypothesis testing. We have done the exercise of the first one, but I'll leave the other 3 examples for you to study on your own. We have some samples here. We will start next week's class by doing these examples together in class. At the end of this presentation, are there any questions about hypothesis testing? Okay, that took me about 50 minutes to go through all that, but the gist of it, too long didn't read, is displayed on your screen right now. How you can formulate the hypotheses as follows.